our discussion of free particle stationary states, traveling waves that are infinite in extent and therefore not normalizable, led us to the concept of a wave packet, and the results of Fourier analysis that described how we could superpose these infinitely extended traveling wave solutions to make something that was localized and therefore normalizable. To give you a feel for what these look like, here is an example. The initial conditions we're going to consider here are something we've seen before in class. The wave function psi evaluated at t equals 0 is given by this conditional expression. You have a normalization constant out front, and then you have values for a x between minus a and 0, between 0 and a, and everywhere else is 0. What this actually looks like is from, say, minus a to a, our wave function is a triangle. And outside of those regions, our wave function is 0. So this is now psi of x at t equals 0. If this is our wave function, hopefully you remember what the probability density as a function of position looked like at time t equals 0 as well. Between minus a and a, it sort of looked like two parabolas joined together. So how would we go about expressing this initial condition as a superposition of these infinite traveling waves? The result from Fourier analysis we're using now is the expression for the phi of k, the representation of the wave function in terms of k, where k is related to the energy and the spatial wavelengths of the traveling wave. What this actually looks like, we have to substitute in our definitions. We have a 1 over root 2 pi as before. From our initial conditions, we have the normalization of the initial conditions, 3 over 2a in a square root sign. And then our initial conditions are split up between the region minus a to 0 and 0 to a. So let's split up our integral from minus a to 0, and again from 0 to a. And we'll be adding these two integrals together. These are going to be integrals dx. I'm just splitting up this integral here. And what we actually have inside our integral, since we're looking at the t equals 0 version of the complex conjugate of the wave function here, e to the minus ikx is all we've got to work with for our traveling wave, and our initial conditions enter in from just the spatial dependent part. So we have a plus x over a from the space from minus a to 0, and then our e to the minus ikx from here. And for the space from 0 to a, we have a minus x over a, and then again e to the minus ikx dx. This is the integral that we wish to evaluate. These integrals are not as difficult as they might seem, because they're all of the form either e to the minus ikx or x e to the minus ikx. This can just be directly integrated. This is a candidate for integration by parts. So those would be the techniques that we would use, and if I had the patience to work through the page or so of algebra, what we actually end up with here are phi of k ends up being sine squared of x over x squared, related to this. It's not going to be exactly x, but this is the sort of functional dependence that we have. Sinc squared, if you're familiar with the definition of the sinc function. Here's what that looks like. This is phi of k as a function of k, or phi as a function of k. So our x-axis here is k, and our y-axis is phi of k. The sinc squared function here is symmetric between negative and positive values of k. What this means from the perspective of the traveling wave solutions is that phi of k, which tells us how much of each traveling wave solution we are going to add up to get our overall wave function, we effectively have equal contributions from left-going waves and from right-going waves. So overall, maybe we expect our wave function not to be moving. Knowing what phi of k is, we can go back through taking the inverse Fourier transform to find out what psi of x and t is, because we know the time dependence of these traveling waves. The inverse Fourier transform then is going to give us psi of x and time, including the time dependence, in our traveling wave solutions now. So we have 1 over 2 pi times the integral from negative infinity to infinity of this phi of k that we got from the previous slide. This is going to look like sine of k, sine squared of k over k squared. So we have a function of k, we have another function of k, and the integral here, which I left off in the actual notation, is dk. So in principle, if we had something here that we could easily integrate, we could find psi as a function of t. Unfortunately, closed-form integrable solutions to this equation are hard to come by. The example I've chosen here, you can probably guess that we're going to end up in trouble because the initial function that we started with, our initial conditions, was defined piecewise. And it's difficult to imagine a closed solution like this that gives us anything sensible that we can work with in the piecewise manner. So, at this point, we could in principle do this integral, but I'm lazy. So let's go and look at what the solutions actually look like. I went through and did these integrals numerically using Sage, and here's what you end up with. The initial conditions, the real part of the wave function is shown in red now, the imaginary part shown in blue. So when this animation loops, there's your initial conditions, and gradually things get smoother, decay away. You start to see things that look like traveling waves propagating to the right and propagating to the left. If I look at this instead in terms of the probability density, this is now a plot of the squared modulus of the wave function as a function of time. The initial conditions look like those joined parabolas there, but gradually things spread out, starts looking like a Gaussian, and the probability density gets broader and broader and broader and broader. So this is what wave packet solutions to the time-independent Schrodinger equation, or for the full Schrodinger equation, for the free particle actually look like. Your initial conditions are expressed as a superposition of stationary states, these traveling wave solutions, with the results from Fourier analysis. Taking the inverse Fourier transform of the representation in terms of stationary states allows us to easily add the time dependence, since we know the time dependence of each stationary state. The final solutions then are often tricky to work with, but in this case we could do something numerically relatively easily, though it did take a bit of CPU time to do these integrals. And you get a feel for what the wave function of evolution actually looks like. To check your understanding, here are a couple of questions. I've gotten sloppy with my notation. This is phi of k, the Greek letter, not phi of k. But first question, the wave function represented in terms of k is symmetric. Phi of minus k is phi of k. What does that imply about the direction of propagation of the particle, or of the wave function? And second of all, you have some spreading out in space. Does the representation of phi, or does the representation of the wave function in terms of k, which is related to the momentum, it's often called the momentum representation, also spread out as time increases?